Hello, and thank you for attending my presentation. The title of my thesis is Evaluation of Machine Learning Algorithm in a Human-Computer Hybrid Record Linkage System. This is an overview about what I'm going to talk about during my presentation. First, I'm giving you the introduction and background about record linkage, and then I'm talking about the hybrid record linkage framework. Next, the experimental design and evaluation criteria, and followed by the result of my researches, and finally the conclusion. What is the record linkage? Record linkage or entity resolution is identifying the same entity across one or more database when there is no unique identifier. The amount of data that is generated in the board grows at an exponential rate. And in that situation, it is very important to have integrated data, because integrated data give us a more complete view of data, more useful insight, and it also can accelerate the research in critical situations. For example, with COVID-19 situation, if we can integrate data from patient data from different hospital or medical center, we can get richer analysis in less time. What is the difference between record linkage and deduplication? Record linkage is finding data that refer to the same entity when we have two or more databases. Deduplication doing the same thing, but when we have only one database. In fact, in deduplication, we link one dataset to itself. There are a lot of applications for record linkage. For example, we can link health data, insurance claim data, registries data, vital statistical data, and genealogical data. Some of these applications are very critical, like health data. And in this domain, we need to have a very high quality record linkage, and having error is not acceptable. So we need to tune our algorithm such that we minimize the error. But in some other area like genealogical data, maybe we have some room for having a small portion of error. So we will see in the future slides that in such situation, we can change our algorithm and get more linkage, but having slightly more error in our algorithm. These are the challenges and issues that we will see when we doing a real-world record linkage problem. Data can express differently. For example, some people use nicknames. Data can change over time. For example, in US, when some women, when get married, they change their last name. There are some common names like John Smith in the US, which is very common and can refer to a lot of people. Some names are very similar to each other, for example, name of twins or family members. And we may have missing data or errors in data like typos, swaps, and other errors. Record linkage system can be classified into three main categories. The first one is manual record linkage. It means a human expert look at the pairs one by one and decide whether they are matched or they are not matched. These systems are very reliable, but they are expensive and very time consuming. The second group is automatic record linkage. In these systems, machine learning algorithms doing their linkage. It is fast and scalable, but it may not be as have a high reliability. Machine learning algorithm actually assign a probability for each of pairs that say, for example, these pairs are 80% matched or these pairs are 80% unmatched. So by assigning a probability between 0 and 1 and having one threshold, it will classify the data into two classes, match and unmatched. The hybrid record linkage is the category number 3. Here, instead of having 1 threshold and 2 class, we have 2 threshold and 3 class. So first, machine learning algorithms do the record linkage and classify data into 3 classes: match, unmatched, and uncertain. Uncertain are the pairs that machines are not sure about that. It means it classified them with less probability. So we need human judgment here. After automatic record linkage finished, we send this class of data to the human expert, and they will decide whether they are matched or unmatched. So we have 2 main goals for hybrid record linkage. The first one is high linkage quality, and the second one is minimizing the manual review size. These are my research questions. I had 3 research questions, and I answered them during my research time. And the first one is how well machine learning algorithms meet the 2 goals of hybrid record linkage. Second one is how well machine learning algorithms that we train them in one data set transfer to a new setting. This is actually very important because one of the difficulties to using machine learning algorithm in a real world record linkage problem is to generating training set with a label. So it would be good if we can use the train model that we train in one data set to another setting. And the last question is how adding name to web, which is a name embedding feature, can change these results from experiment 1 and experiment 2. So as a contributions of my research, we propose a hybrid open source record linkage framework that can achieve scalability and high quality result. We compare 4 different machine learning algorithms in terms of the goal of hybrid system and also how well they transfer to a different setting. And the last one is evaluating the impact of name to web feature to machine learning, to the performance of machine learning algorithm. This figure shows the hybrid record linkage framework. As you can see, we have 2 main parts here. The first one is automatic record linkage, and the second one is manual record linkage. Suppose we have multiple databases that we want to link them together. The first step is generating pair from them, and then we are going to extract some useful feature. After that, we feed this feature to machine learning algorithm. Machine learning algorithms are going to classify this pair into 3 classes: match and unmatched and uncertain. Match and unmatched are going to result directly, but the uncertain part is going to manual record linkage. In manual record linkage, first 2 reviewers review the uncertain pair and individually and record their decision. If they were agree about that, it's going to result. If not, it means one of them says they are matched and the other says they're not matched. We need 2 other reviewers to review this pair. And if still there is disagreement, we need an open discussion, which in it, all of 4 reviewers discuss with each other and decide about this pair. The first step in automatic record linkage is generating pair. There are different approach for generating pair. The first one is naive approach, which means we pair every record in one data with every record in another database. This approach is very simple, but it may generate too many pairs, and most of them are very different from each other, and we don't really need them in our process. So we can use blocking. It means we block the block the record and generate pairs that have a common attribute. We can block on one or more attributes. For example, here, this pair is generated by blocking on last name and date of birth. In this way, we can reduce the computation, but maybe we miss some matches. For example, there may be some matches in data that has typo in the last name. For solving this situation, we can use multipass blocking. In multipass blocking, we are going to do the blocking several times. Each time we block based on one or more attributes. For example, in blocking 1, we can block the data based on first name and last name. In block 2, we can block it based on first name and date of birth, and so on. After that, we aggregate this data, delete the duplication, and get the final pairs. After generating pair, the next step is extracting some useful feature. For extracting feature, I use similar distances. The first one is Jaro-Wickler distances, which is based on Jaro similarity. Jaro similarity measuring the common character in a string that are not very far from each other. And Wickler modified this algorithm to emphasize that the difference at the beginning of the string is more important than the difference at the end of the string. The second distance is the Merrill-Levenstein distance, or DL distance, which is the minimum number of operations required to change one word to another word. And these operations are include insertion, deletion, substitution, and transposition. For example, here, suppose we have these two strings and we want to change one of them to another. First, we need to substitute K to C. Then we are going to add E after H. After that, we are delete the Y and transpose NI to IN. And finally, we insert an E at the end of this string. So because we had 5 operations to change one string to another one, the DL distance is equal 5. Longest common subsequence distance, or LCS distance, is very similar to DL distance, but here we only have 2 operations, insertion and deletion. So for the example that we had at the previous slide, we need 7 insertion and deletion operations. So the LCS distance is equal to 7. SoundX code. SoundX code is a phonetic coding algorithm for indexing name. The application is for the name that we spelling differently, but we pronounce them in the same way. For example, Robert with O and Robert with U. For creating a SoundX phonetic code, we use the first letter followed by 3 digits that can be computed based on this table. There are other rules. For example, we disregard these letters A, E, I, O, U, H, W, and Y. For example, for Robert, we get the first letter R. We disregard O. B is 1. We disregard E. R is 6. And T is 3. So the SoundX code is equal R163. If 2 names has same SoundX code, the SoundX distance between them is 0. Otherwise, it is 1. And the last distance that I use is name to vec distance, which is a name embedding based on doc2vec. But here, each name is a document and each letter is a name in a word. So name to vec is going to embed the name into a vector space and then calculate the cosine distance between them. We used the name from 2 public US datasets and trained 2 different models, one for first name and one for last name. Then we use this trained model to generate the name to vec distance for our pairs. So based on the distances that I introduced in previous slides, we extract some features from different attributes. For example, for names, we extract JW distance, DL distance, LCS, name to wake, and sound distance. We also generate a normalized frequency, which shows how rare the name is, and also minimum and maximum lengths, and a flag that shows if first name and last name are swapped. I think Dr. Fawcett has some problem to hearing me.
But I think he said that it's okay, and he turned off his video to facilitate. So I think you can continue.
Okay. For date, we extract the DL distance for the whole day, DL for year, month, and day individually. Also, we use year to compute the age and a flag that shows if day and month are swapped. And for address, phone, and social security number, we extract DL and LCS distance. Also, we have gender code that shows whether the gender of two records are the same or not, and potential marriage for women over 18 years old, which change the last name or have a different last name in the records. After extracting features, it is time to feed those features to machine learning algorithm. This figure shows the general framework for machine learning. First of all, we split the training data set into two-part training set and validation set. Using the training set, we are going to train multiple models with different hyperparameters, and using validation set, we tune our hyperparameters. After that, we train one more time on the whole data set, and using the best hyperparameter that we get from here to generate our final model. Then we can evaluate this final model using the test data, which are the data that we didn't see during the training. I use 4 different machine learning algorithms. The first one is random forest, which is a tree-based ensemble model. Each of these trees are going to generate one label for the input data, and we can get the final result by majority voting. And for tuning the hyperparameters, we use temporal cross-validation. The next one is support vector machine, which is the maximum marginal classifier. The goal is to find the boundary decision such that this class sample have the maximum margin. This maximum margin can cause more confidence decision in a new data. 2 support vector machine has been trained in our study. The first one is radial SVM, and the second one is linear SVM. Again, for tuning the hyperparameters, we use temporal cross-validation. Dense neural network is the next machine learning model that we use, which is a nonlinear classifier. We use 20% of data as a validation set, 20 epoch, RMS prop optimizer, and binary cross entropy loss function. As an input layer, we have 33 units, which are the 33 features that we extract from our data. Then we have 2 hidden layers with ReLU activation function, followed by 1 output layer, which is 1 unit with sigmoid function, and give us the probability of being matched for each of the pairs. For our study, we use two real-world data sets. And the first one is hospital EHR data that we used for training. And the second one is North Carolina voter registry data that we only use for testing our model that we trained using EHR data. EHR data is a big data set with 10 million pairs that generated by first name and last name, first name and date of birth, and last name and date of birth, and social security number. 20,000 pairs were randomly selected as a gold standard data set and reviewed by 4 experts to generate the labels. We use 10,000 of these data as a training set and 10,000 for test set. There are 630 linkage in the test set that we want to find. For record linkage, we use 7 attributes: first name, last name, date of birth, gender, social security number, phone, and address. North Carolina voter registry data is a public database that can be downloaded from this link. And this data is only used for testing the model that we trained based on EHR data. We generated 10,000 pairs from Yancey County from 2 time point, May 2017 and July 2020. We generate our pairs by blocking on first name and last name, first name and date of birth, and last name and date of birth. And we use the voter registry number as a label. For evaluating our model, we used manual review size, a phone score, and recall. If we consider these confusion matrix, we can compute the precision, recall, and a phone score with this equation. For a phone score, we only use the result from automated part, which means we only consider the pairs in the green and red area. But for recall, we use the whole data because we want to see how many of true positive our algorithm catches. As I said before, in hybrid record linkage, instead of 1 threshold and 2 class, we have 2 threshold and 3 class. So we need to select this threshold because we are working with health data and we want to have as minimum error as possible. We select the threshold such that the positive predictive value and negative predictive value is equal to 1. It means we had the perfect prediction on the training set. We designed 3 experiments to answer our 3 research questions. The first one is comparing the performance of different machine learning algorithms. In this experiment, we only use EHR data. We use 10,000 pairs of EHR data as training set and 10,000 pairs as test set. The second experiment is to compare different machine learning algorithm in terms of transferring to new setting. For this, we use the trained model that we got from first experiment and test that on the North Carolina dataset. And the last experiment is the effect of name-to-vec feature on model performance. So we add the name-to-vec feature for first name and last name and repeat experiment 1 and 2 with these features. These are the results of my research. This table showing the result of experiment 1, which were comparing different machine learning algorithms in EHR data. As you can see, random forest and linear SVM has the biggest F1 score. However, they only could catch 60% of true positive. And also they had more manual review pairs than 2 others. So we can conclude that radial SVM and dense neural network has better result overall because they catch more true positive data. They have a smaller manual review size, but still they have a reasonable F1 score. The second experiment is to see how this machine learning model can transfer to new setting. So we test them on North Carolina voter data. As you can see in this table, random forest, linear SVM, and radial SVM transfer much better than dense neural network. For these three models, also we have the bigger manual review size rather than the experiment one, but still we have a good performance in terms of F1 score. The best result is obtained by radial SVM. As you can see, the recall is 80%. So 80% of true positive pairs were cached by the machine learning algorithm. Dense neural network is not usable here because we had a lot of false negative and false positive, which is not acceptable. And it may show us that dense neural network is somehow overfitted to EHR data and couldn't transfer to new setting well. We rerun this experiment 100 times, and in this table, we report the mean and standard deviation of the results. And finally, as our last experiment, we added two features to our data: name to vec for first name and name to vec for last name. As you can see here, adding name to vec can cause a big reduction in manual review size and significant increase in the recall, but the F1 score didn't change much. And this result that I said is true for all of the algorithms except the dense neural network. In dense neural network, we have a little increase in manual review size, but also we have a little increase in F1 score. And we did this experiment in voter registry data too. In voter registry data, you can see that the radial SVM benefited the most. We have a big reduction of manual review size here and a small change in recall overall and F1 score. We cannot see a significant change in the manual review size for two others, random forest and linear SVM. And also here, we can see the big reduction for recall in linear SVM. It means that we couldn't catch many true positive for linear SVM. As a conclusion, we can say that overall the SVM model, especially radial SVM, performed best in all experiments. Random forest, linear SVM, and radial SVM transfer better to new setting rather than dense neural network. And adding name to vec can cause a big reduction of number of pairs that needed manual review. It can improve the recall overall, but with only a slightly change in F1 score. So the choice of using name to vec feature or not using it, it totally depends on the application that we have and depend on how much error do we allow to have in our process. The code and models of our open source record linkage framework can be downloaded from this GitHub repository. User can use our trained model and use them to test their data, or they can train their own model with using their own data. And the result of our study has been accepted as a conference paper in AAAI Make, which is a computer science conference on combining machine learning and knowledge engineering. And as a future work, we need more research to see which characteristic of SVM model can better performance in hybrid record linkage. And we also need to test more complex neural network models to see if they can transfer better. I would like to thank my advisor, Dr. Haitran Kuhn, for all of her support and help. Thank you, Dr. Kuhn. Every time that I had any problem or I didn't know how to continue my research, you always spend time and sit with me to find a way to continue. Thank you so much. I really enjoyed working with you and I learned a lot. And I also want to thank my committee, Dr. Da Silva and Dr. Fawcett. Thank you for your time and for your interest in my research. I'm really interested to see your feedback and comment about my research. Also, I want to thank my family, my mom, my dad, my sister, and my husband who's here. I'm really lucky to have them in my life. Thank you so much. I love you. The funding of my research is from PCORI and NSF. I also use VIDAL, which is a virtual data library for Texas A&M University. I use it for collection management and analyze my data. And I guess this is the end of my presentation. Thank you.